First of all, let me introduce myself. My name is John Renton. I'm professor of geology at West Virginia University, and I'm here to teach you something about Earth. Now, it's customary to start a course off like this by giving some statement as to what my intent is. Most teachers do that. And let me tell you what my intent is not. My intent is not to turn you into a geologist, because I'm sure you have a profession of your own. But about several weeks ago, I received an email from one of my former students that I think spells out beautifully just what my intent really is. This student was in my class 30 years ago, now lives in California, as you'll see in a moment. And here was his email. We had a shake here a few minutes ago, a jolt that rocked the house and told me the epicenter must have been close by. Checking the USGS website indicated it was just off the Golden Gate, 8 miles down. But this time I was on my computer, and I thought I'd Google you up and tell you how fortunate I feel for having taken your classes in geology in 1973 when I was a freshman at WVU. Though I never became a geologist, I often draw upon what you lectured about when I'm cruising around California, which has some of the most dramatic terrain in the world. I can explain to my daughter why this beach has sand and that beach has rocks, or how it is that rivers' courses are the way they are. Well, she thinks I'm pretty bright. But in fact, I'm just passing on what I got from physical geology. To finish, I'd just like to say that hardly a week passes that something doesn't cause me to think about your classes. And so I think that really spells it out. What I'd like you to get out of this course is information that you will take with you for the rest of your life, wherever you go in the world. I don't care whether it's a trip to the office or on vacation, so that you can look at the world that passes you by in a little bit different fashion, understanding it better, appreciating it better. So if you do that, then my intent will be fulfilled. Now, the other thing I'd like to do is to give you some idea of what the overall course is going to be like here. And I divided this course into 12 topics. The first topic is going to be called Earth and its place in space, because I think it's very important for students, for anybody getting into a course in geology, to have an idea of where you fit into the big picture. And of course, the big picture is going to be the universe. So we'll do that first, and then we'll go into the two sections on rocks and minerals. You have to understand what the Earth is made of, and so we'll talk about minerals first. And there are thousands of these things, but you're going to find out there's only a handful, a couple of dozen, that make up almost all the rocks of the world. So it isn't really very taunting there. The next one's going to be the rocks themselves. There are three basic kinds of rocks: igneous rocks, metamorphic rocks, and sedimentary rocks, and we'll go through each one of those and explain how they form and where they come from. And then we'll go into one that students often like to talk about, volcanism. This is probably one of the most spectacular features that are happening on the Earth today. Not so much in the East, of course. We don't have it in the East, but in the West, there's lots of volcanism going on. Those of you who might have traveled to the northwest of the Cascades, we'll talk about that. And then after that, we're going to go into a series of lectures, the ultimate goal of which is to describe how the land has come to look like it does. Surely in all your travels, you know that land changes its appearance. You don't have to go very far because the topography looks different. Well, for the next few topics, we're going to talk about things like mass wasting. Mass wasting, I always say, is the unsung hero of all geologic processes, because it goes on without most people knowing it's even going on. And then we'll go into perhaps one of the most important of all the geologic processes that are happening out there. It's called weathering. Weathering is the process whereby rocks either decompose or disintegrate into bits and pieces to be carried off, dumped into the ocean, and created into a new rock, usually into a sedimentary rock, but we'll get to that. And a part of this topic, we're going to talk about soils. Now, the reason why is because soils are made from the products of weathering. And the reason why I want to take it up in this course is because without soils, you and I wouldn't be here, and you'll see why when we get to it. Then finally, we'll talk about the sculpting of the land. The processes that do the sculpting we call erosion. Streams are the number one. Anywhere you go, anywhere that water can exist, streams are the number one agent of erosion. So when you go out there and you look at the land, most of what you're looking at is the result of the combination of mass wasting and streams having done their thing. But there's also glaciers where they exist. They're very, very good. It just obviously they don't exist very many places except where it's cold. And then we'll finally go into the wind. The wind is sort of number three, but it's a distant number three. It's given credit for doing an awful lot of things it really doesn't do, and we'll talk about that. And then the next topic I take up, I'm going to talk about groundwater. Now, I had to pick and choose as to what we were going to cover in the course. I picked groundwater because this water now provides half of all the drinking water in the United States. And it's going to become more and more important as years go on. And we've got to remember that it's a non-renewable resource, and we've got to protect it and use it wisely, something we've not been known for in the past. But anyway, I want to talk about groundwater so you have a real feeling for what that's all about. And then I'm going to go into the last three topics are going to be rock deformation, earthquakes, and mountains. They all sort of go together. Rock deformation is just what it says it is. Breaking and bending of rocks. Earthquakes are the result of some of the breaking of rocks, as we'll find out. And then we're going to complete the course with a discussion of mountains. And the reason why I have this at the end, in my way of thinking at least, mountains are sort of the last remaining thing of all the totality of all we're going to talk about. It's the epitome of what geology is all about. It's all the processes we'll have talked about working together and making what has to be the most spectacular thing on the Earth's surface. So anyway, that's what the course is going to be about. And where to start? I've often thought that the place to start a course in geology is in the beginning. And in the beginning, the astronomers tell us there was no need for geology, because there were no rocks, there were no minerals, there was no Earth, there were no stars. They tell us there was nothing. So my question would be, what about all this stuff out there in the universe? Where was it? Well, that depends upon to whom you speak. There was a Belgian astronomer named Lemaitre who said that all the stuff we now see in the universe, not all of it, was once crunched down, possibly into a sphere about the size of a golf ball. Now, obviously, whatever was in there wasn't matter as we know it. The conditions would have had to exist in there would not allow matter to exist. It would have been ripped apart. Even the stuff matter is made would have been ripped apart. Atoms and things like that. Question, what was in there? Well, they say that what was in there were things called quarks. And what a quark is, according to a physicist, that's the smallest subdivision of matter. So in his case, he called that the primeval atom. His primeval atom was filled with quarks. Now, if that's not a good enough theory for you, here's another one. The crunch could even go further down to what is referred to as a singularity. A singularity, by definition, is a non-dimensional spot. What's there? Nothing but energy, just pure energy. And then what happened? Well, according to the theories, what happened then was an event that we usually refer to as the Big Bang. The Big Bang, what was it? Well, it again depends upon whether you believe in the primeval atom or the singularity. In the case of the primeval atom, the picture is that it exploded. In the case of the singularity, it just started to rapidly expand. Well, let's go to the primeval atom. When this thing exploded, all of a sudden, picture rushing out into space in all directions, these quarks. Now, there are 6 kinds of quarks. This physics has interesting names to these things. Up and down, charm and strange, top and bottom. Don't ask. But anyway, the two are going to be important to us are the ups and downs. Because these are the two that are going to go together to form the 2 fundamental components of atoms, namely protons and neutrons. Now, here's the way it works. The ups are worth plus 2/3 charge. Each up is a plus 2/3 charge. Downs are a minus 1/3 charge. So the way it works is, if you have 2 ups and 1 down, that's 2 times 2, 4/3, plus 1/3 down. If you subtract the 2, you end up with 3/3, which is 1. That forms the proton. That's why protons have charge of 1. On the other hand, if you have 2 downs, minus 2/3, 1 up, plus 2/3, they cancel each other out, and you have no charge, that's called a neutron. So your protons and neutrons are formed from the ups and the downs. And then, of course, what happens to the electrons, they simply are bundles of energy, and we know how that works. Now, the way it works then, now we have protons and neutrons, and these things go together to form the most fundamental atom of all, namely the hydrogen atom, which is 1 proton surrounded by 1 electron. Now, there were neutrons made into helium-2, but apparently there was not very much. The neutrons were used up very, very fast. So in our discussion, we're going to be talking primarily about the generation now of hydrogen atoms going out into space. Protons were being created. Out of the energy alone, electrons were being created, because that's all electrons are, just little bundles of energy. That would have happened with the primeval atom. How about the singularity? There wasn't anything there in the first place. Well, you got to make some matter. And how do you do that? Well, according to Albert Einstein, you can take his equation, E equals mc squared, and take energy and turn it into matter. And I presume the matter it was turned into would be the quarks. So in either case, we're forming the quarks, rushing out into space, and then the quarks started getting together to form the basic fundamental parts, protons and electrons. And then they say within probably a half an hour, which always cracks me up in a way, thinking about something that 13.7 billion years ago were broken down into half-hour segments. But they say within a half an hour, these things started getting together to make the most primitive of all atoms, a single proton, surrounded by a single electron, of course, hydrogen. So now if you could just imagine this bubble, if you will, of hydrogen roaring out into space in all directions. What was the next thing that happened? Well, the astronomers say little bundles of hydrogen started getting together. And I never could quite find out what caused them to do that, but they talk about these little bundles of hydrogen that started rotating on themselves. Now, I do know this. Isaac Newton taught us that in space, if you start to turn, which they were turning, you see, a force of gravity was generated perpendicular to the direction they were going, pointing toward the center of rotation. So picture now these little bundles of hydrogen starting to rotate, collapsing on themselves down into some core, and as they collapse down, some of that gravitational energy is being converted into heat. And they say that whenever the heat got up to about 15 million degrees in whatever measurement you want, what happened down in the core is 4 hydrogen atoms got together with 4 electrons to form 1 helium atom. Now, if you look at the mass of the 4 hydrogen atoms and the mass of 1 helium, 4 hydrogens has more mass than 1 helium. So it looks like we had some mass lost here someplace. Well, again, they tell us you can't lose mass, but you can convert it, according to Einstein's equation again. So that little bit of lost mass was converted into energy. So in addition to the helium, you're giving off all this energy, and of course, what we've got now are stars. That's how stars were created. And stars were created through this expanding cloud of hydrogen gas. How much long it went on, we don't know. Maybe a million years, who knows? But sooner or later, the number of stars became so numerous that they started to attract each other. Because again, Isaac Newton taught us that everything in the universe attracts everything in the universe. So they started attracting each other into huge groups of stars called galaxies. Now, how big's a galaxy? How many stars? I really hadn't the slightest idea. Probably billions and billions, as Carl Sagan would have said. Maybe 100 billion, maybe 150 billion into this huge group, and then it started to rotate. Now, things rotates like that starts to flatten out along the rotational axis. I think you probably remember from somewhere in your education that the Earth was, 27 miles shorter in the rotational axis than it is in the equatorial axis? Well, in this case, this mass of stars started collapsing down to form a discus shape. Now, there are all kinds of galaxies, I know, but the astronomers tell us that the general shape of a galaxy is a discus shaped. Most of the stars being located at the center, as you might suspect, and as you get out to the outside edge, the number of stars get fewer and fewer and fewer. Well, of course, we belong. When I say we, our little private star, the Sun, belongs to one of these galaxies. We belong, of course, to the Milky Way galaxy, and we're located not all the way out to the outer edge, but pretty far out to the outer edge. It's sort of a neat place to be because it's sort of like standing at the edge of the woods. You can look beyond the edge of the woods, across the field to the next woods on the other side. Well, in this case, we can look beyond the edge of our own galaxy, across space to the next galaxy, which is Andromeda. Had we been in the middle of the galaxy, I suppose we probably couldn't have done that because the stars would have gotten in the way, like the trees would have gotten in the way if you were standing in the middle of the woods. So anyway, now we have this galaxy rotating us on its own axis. Galaxies started to form. How many galaxies are there? Well, again, I really don't know how many galaxies there are. Billions and billions, maybe 100 billion of these things, all rotating on their own axis, all rotating around space, around some point in space, I presume, where the Big Bang occurred, and all moving away from each other. Why? Because the universe is still expanding. We're still in an expanding universe. Question, how long will that go on? Well, again, I think that depends upon to whom you speak. For example, it depends upon how much matter is in the universe. Now, here's the real problem. We don't really know how much matter stuff is in the universe. We can see some of it. We can see stars. We can see planets. We can see those. But then there's the stuff that they call dark matter. We can't see dark matter. What dark matter is just bits and pieces of stuff we're going to talk about, cosmic dust. They're not big enough to give off much light. They don't give off their own light, so we really can't see them. So we call that dark matter. So the idea is that there's, they say, a critical mass of stuff. What that is, I've never had anybody explain to me exactly what critical mass is, but it has to be something beyond which something happens. Well, in this case, they say, if the known amount of mass we can see and the dark matter is less than this critical mass, then they say what will happen is the universe will expand forever. And then what's going to happen? Well, picture the universe expanding forever. It's expanding into space. There's no limits to space. So sooner or later, galaxies are going to get so far away from each other, you're not going to be able to see one from the other. And as they get further away from each other, as we're going to see for long, I'm talking about stars, the stars are going to start dying. And pretty soon, the universe is going to turn into a very cold, dark, dismal place. Not a place I'd think I'd like to be in. But that's if it's an expanding universe. That's called an open universe. On the other hand, if the total amount of known matter and dark matter is greater than this critical mass, what's going to happen is the universe is going to expand until a point is reached when gravity takes over and it says, okay, that's far enough, let's all go back. Now what we have to do is to crunch back, and just picture this now, as the universe collapses on itself, a general term for that is the Big Crunch. This would be the way universes die. What's going to happen? Galaxy is going to crash into galaxy. Star is going to crash into star. Any planets around those stars are going to be in big trouble. And it's going to crash back to, guess where? It's going to crash back to, perhaps, that primeval atom of Lemaitre, or maybe back to that singularity. And then what do you think will happen? Just a gut feeling what's going to happen. It's going to do it all over again, because the concept of this one is that it's a cycle. It's a big cycle. Now, part of that theory says that we might not be the only universe. Out there could be other universes, some expanding like we are, some undergoing the Big Crunch and dying, others having just got back to the singularity or the primeval atom ready to start again, other primeval atoms or singularities ready to start. And so the idea is that we're not the only ones out there. And that sort of gives me sort of a fuzzy feeling to know that. So that's if we have the critical mass exceeded by. On the other hand, of course, if the total amount of known and dark mass equals a critical mass, they say that's the flat universe. It'll simply expand and come to an end, but it will never collapse on itself. So anyway, which one of those you want to believe, it's up to you. All right, so now we have the galaxies. But I think we want to talk about stars, because stars now are very, very important. They have an importance that most people don't know. For example, if it wasn't for stars, you and I wouldn't exist here. Okay, the stars, let's go back. What a star is very simple. It's a thermonuclear reaction where 4 hydrogen atoms are being put together to make 1 helium and release all of this energy. Now, classification scheme. I looked about a lot of classification schemes of stars, and I always picked the easiest one. And the easiest one had 4 different flavors of stars. The flavors were flyweight, lightweight, middleweight, and guess what? Heavyweight. Had to be put together by a boxing fan, just had to be. Now, the unit of measurement used to determine which of those categories you're in is the amount of mass in our own sun. So they have what we call a solar mass. And the way it works is the flyweight stars, the little ones, are those that are less than a half of a solar mass. Then the lightweight stars would be from a half up to about 4 solar masses. Now note, our sun with 1 solar mass is down at the short end of that thing. So our sun is actually a fairly small star. Then the middleweights would be from 4 solar masses to about 8 solar masses. And then the big guys would be anything over 8. And how big they get, I read an article recently where they were talking about a star of 100 solar masses. That would be really, really pretty big. Now, here's an important point, too. These are fires we're talking about. We're talking about burning hydrogen and turning it into helium. Now, I don't care what kind of a fire it is, whether it's a fire in a star converting hydrogen into helium or a log in your fireplace converting the log into heat and ash. A fire is a fire is a fire. Eventually, it's going to go out. So in other words, stars have lifetimes, life expectancies. The question is, of those 4 categories, which one do you think would last the longest? Well, no, this is a question I always ask my students, and invariably, they always pick the big one. Matter of fact, that's the one I picked too when I was a student. It just seems so simple to me. With all that fuel, it's going to take an awful long time to burn it all up. Well, that sounds good, but that isn't the way it works. Apparently, the big stars have a lot of fuel, but they burn it at a very, very high rate. No, it turns out the smaller you are, the longer you're going to live. For example, those little flyweight stars, it's estimated that the minimum age for those, minimum now, would be something on the order of 50, 55 billion years. Well, note the universe has only been around for 13.7. So that means that any flyweight star ever created is still there. They haven't had enough time to go by to have any of those guys die. To give you some idea, our sun is given a life expectancy of about 10 billions of years. The astronomers say it was created 5 billion years ago, so our sun is now coming into midlife. About 5 billion years to go. Those big guys, those big ones, 100 solar masses, they might not even last 1 million years. So that gives you some idea of time. But I think probably how they die is more important than how long they live. How are they going to die? Picture the core of this star now. Most stars spend 95% of their lifetime in what is called main sequence. Main sequence means you're burning hydrogen, you're converting it into helium and releasing all that energy. But know what's happening down in that core. You're taking hydrogen atoms, atomic mass 1, you're converted into helium atoms, atomic mass 4. So you're making more massive atoms out of the light ones. Well, again, Isaac Newton taught us that the gravitational force is a function of product of masses. And so the idea is down in that core, as it becomes more and more enriched in the helium, the core starts to collapse on itself and starts to heat up and is heading toward what is known as a white dwarf. Now, the white dwarf, the white stands for the fact that the temperature is white hot. So it's a temperature thing. The dwarf part refers to the size. It's estimated a typical white dwarf might be the size of our Earth, so about 8,000 miles in diameter. In the case of the flyweight stars, remember now, none have died, but they say when they do, that's the direction they're going to go to. They're going to go down to a white dwarf, and then finally all the fuel is going to be burned up, and they'll just sort of go out, nothing spectacular there. But what happens in the other 3 is much different and much more important. What's going to happen now is their cores start to collapse down, generating enormous amounts of energy. Remember now, there's more star stuff around the core of these stars, and it gets blown out perhaps 100 times the original diameter of the star. Now we got a giant star, and now the temperature on the outside cools off a little bit, the red heat. So we have the red giant phase of star evolution. Now, the important thing in the red giant phase, think about that core now. A lot more energy in the core. Up until now, you've been converting hydrogen into helium. Now helium starts to be converted, acting as the fuel, into bigger atoms. The biggest atom, as I remember, can go out on the periodic table to atomic number 26, which is iron. But the 2 I'd like to comment on, carbon and oxygen are created during the red giant phase. What's the importance of carbon? All life as we know it. You and I are carbon products, you see. We're carbon products. Just think about this now. Every carbon atom in your body and in mine was created out there in the red giant phase of a star's death. That's pretty awesome. Oxygen. Now, I always bring this one up because I remember so many students always say they think oxygen is created by green plants. Well, no, not quite. Not quite. The way green plants work is they take, of course, water, carbon dioxide, in the presence of chlorophyll, catalyst, and the energy of the sun, and they convert it into sugars. Now, if you look at the chemical formula for sugar, and you look at the formulas for water and carbon dioxide, in the combination of carbon dioxide and water, there's more oxygens than in a sugar molecule. Well, in other words, when they make that sugar, they got oxygen left over, and they got to get rid of it, and so that's the oxygen they give up, but they do not create it. Every molecule of oxygen you breathe into your body and I breathe into mine is made out there in the red giant phase of a star's death. Then what's going to happen? Well, then they say it's going to collapse on itself, this red giant, very, very rapidly, very rapidly. And as it collapses down, it's heading toward the white dwarf. Now, in the case of stars like our sun, and maybe in the smaller middleweight stars, that's probably what's going to happen. It's going to collapse down to the white dwarf, and then the white dwarf is eventually going to burn out. But what happens to the other one, the larger middleweight stars, and certainly to the big guys, what's going to happen is they're never going to get that far. They're going to crush down, the energy will be so extreme, they're going to explode and form a supernova. Now, here's the importance of a supernova. All of the other elements that we know, natural elements, are going to be created during the supernova. And if from your chemistry, you remember there are 92 natural elements. From number 1, which is hydrogen, to number 92, which is uranium. All the ones beyond that on the periodic table, those are all created as a result of nuclear reactors. They don't occur in nature. But 92, all the 92 elements are created, most of which, many of which at least, are going to be used to make the rocks and minerals. But here's the point I'd like to make. As an undergraduate, I was a chemistry major. I got my undergraduate degree in chemistry. All the chemistry courses I ever took as an undergraduate, and even the graduate courses I took in chemistry, not once did any instructor ever tell me where the elements came from. I had a course entitled The Periodic Table. I had to memorize the periodic table. I had to know every element and everything about it, but never once did anyone ever tell me where they came from. Where else but a course like this would you learn that? So there's where they come from. They come from the deaths of stars. Then what happens, what's left over from those big guys? Well, it depends. Depends upon how much mass is left down there in the core. Could collapse down to the point we form called a neutron star. Picture this now. The crush is so great that electrons get forced into protons, making, of course, a neutron. That would be a neutron star. On the other hand, you can crush down so far that the thing gets so massive, the force of gravity is so great, nothing can be released from it, not even light. And that's how they think black holes start. So anyway, there's your theory. Then what happens? Well, the end product, of course, is going to be the remains of all this stuff. All these dead stars are going to be blasted out into space, into the cosmos, which is just a fancy word for space. And we're going to create cosmic dust. What's cosmic dust made of? Well, it's made of all the products of those deaths we talked about. There are going to be bits and pieces, for example, of metals, because there's a lot of metals being created. Here, a little bit of trivia for you. I love trivia. Bit of trivia for you. The most abundant single metal in the universe, metal now, is iron. So you got bits and pieces of iron out there, probably copper and all the rest of them. Elements like to get together to form minerals, so there are bits and pieces of minerals out there. Minerals like to get together to form rocks. There are bits and pieces of rocks out there. Now you put those together, that sort of mixture, those are all very dense things, heavy and dense. Well, the density of all that probably averages about 6. But in addition to that, remember, you had an enormous amount of gas. You had all that hydrogen left over. You had oxygen being created. You had helium. You had all carbon dioxide, things like they get together, carbon with hydrogen to make methane. So you had lots and lots of gas blasted out there into the cosmos. But remember now, the temperature out there in the cosmos, what is it, 2 degrees above absolute. So when this gas goes out, it freezes into bits and pieces of ice. So we have what we just referred to as the ices. And the ices are simply bits and pieces of all those gases. Now it's all mixed together and forms this stuff we call cosmic dust. Cosmic dust now fills all the space in between all the stars. So that's what's out there, that dark matter we talked about. Basically, that's what that is. It's cosmic dust. So note we have then a mixture of very dense materials, the rocks, the minerals, and the metals. And then we have the very light materials, all those frozen gases, all mixed together in the cosmic dust. What's the importance of cosmic dust? The importance of cosmic dust is that's where the planets come from. And that's what our next topic is going to be. How are the planets created like Earth? Stay tuned. That's the next topic.